Today, I'll be presenting the paper evaluating fuzz testing. So, let's go over some background information on fuzzing first. So, this paper describes this core fuzzing algorithm right here. I've drawn a simple illustration. You just have some initial seeds, empty, non-empty. You put those into the queue. Then the fuzzer chooses a random candidate or whatever method you use to choose. It then goes through a mutator, becomes mutated, and then you evaluate it to see if anything interesting happened or a crash, ideally. And if any of that happened, you take the mutated output, put it back into the queue so you can further expand upon it. And if you see anything interesting, you want to preserve it. Maybe you want to reuse it as seeds. Maybe there is something interesting that didn't crash the program. And usually you'd stop based on some arbitrary progress or timeout that the programmer chooses. So this paper describes a set of fuzzing guidelines for evaluating fuzzers. These are the four. We'll go through each of them one at a time. So the first one is using statistical tests and performing multiple trials. Regarding statistical tests, the main one the paper mentions is the Mann-Whitney U-test. The reason why is because it's a non-parametric test, so it makes no assumption about the distribution of the algorithm's performance. It makes no assumptions about the data set. There's some other tests they mentioned, like the permutation test, bootstrap based test. If you want to learn more about those, feel free to read the paper, but I'll mainly be focusing on the Mann and Whitney. So once again, why are we using this? It's because we don't know the distribution compared to something like the two sample t-test where the data would have to follow a normal distribution. So you use it for skewed data like this. We don't, it could be normal, but you don't want to make the assumption, especially with low sample sizes. To better explain the Mann-Whitney U-test, as it's never in-depthly explained in the paper, here's a sample distribution with some random data. The average for A, the number of crashes, is 6.1. B is 8. So does this mean that A is better than B at finding the number of crashes? Well, let's do the test. You would combine all this data and then you would rank it. I'm doing all this just with the Google Sheets formula equals rank.average. Then you would give the rank back to the individual groups. So this is just all, oh, sorry. This is just all this data put here. And you would simply calculate it. You take the sum and then you would calculate the U using this formula. What does all of this mean? Like what did these numbers mean? Well, you would take it to a critical table that you can just look up online, Mann-Whitney U critical table test, and recall our smaller value. You take the smaller value of 47.5 here, and you compare it to the critical value in the table, which is 30. It's greater, so there's no statistical difference between the two data sets, and you can't make any claims that one fuzzer finds more crashes than the other. If it was less than, then that is statistically significant. But since it's greater than, you cannot make the claim. So that's some basic statistics background knowledge that you would need to understand how the Mann-Whitney U test works. But is this like the best type of test? Is there some other test that is better? Uh, Doing more research, it looks like it's fine and it's still used because fuzzer data is usually skewed due to having small sample sizes, which leads to random outliers, just due to the randomness of fuzzers. There could be better tests, like if you paired runs that use the same seeds, then maybe a Wilks signed rank test may be more appropriate. But I won't go too in depth about all these different type of tests because there's other evaluation factors. Here's an example statistic to show why doing a statistical test is important. So you can see blue is AFL, red is AFL fast, solid line is the median. If you can see here, this blue dot line, this is just one of the runs of AFL. If you did not do multiple tests or you didn't calculate to see if the results were statistically significant, you might incorrectly conclude that AFL and AFL fast might perform the same, or maybe you only do one run of AFL fast and you get this low red dotted line here. Maybe you conclude AFL is better at finding crashes than AFL fast. Even do, if you do a statistical test with enough runs, you get a p-value that is very extremely small, so therefore it's statistically significant. And now you can conclude that, at least for this target program, AFL generally finds less crashes than AFL fast. Another important factor in fuzzing performance and evaluating fuzzer performance is the seed selection, as picking different sorts of seeds can lead to very different behavior. If you pick one seed set, you might get many crashes. You pick another seed set, you might get 0 seed crashes. The paper mentions that seeds should be disclosed so that these experiments can be reproduced later on. Here's some examples see there, not to go too in depth, but just to illustrate. I will explain everything about this table, but let's just look at AFL naive here. On an empty seed set, it found 0 crashes. And with one seed that they made, which they explain how they made it in the paper, it found 5,000 crashes. So that is a really big difference and statistically significant, as you can see here with this number in the parentheses. So that seed has a large effect on evaluating a fuzzer's performance. However, the paper also talks about empty seeds, and it asks the question, will empty seeds do well on programs that haven't been tested yet? Because if it does well on an empty seed, it theoretically can do well on programs that we don't know much about and don't have seeds already pre-collected. Furthermore, it takes a significant variable out of the configuration space. So that's just another thing you don't have to account for when you're trying to evaluate performance. However, I asked the question, is this a good idea? Because even though it makes it easier to compare the performances because you take out a variable, if fuzzes perform better generally with seeds, it would make more sense to test with seeds, because why would you test without seeds if you don't find as many? You know, so that's pretty much all for the first part. The second part is they mentioned to consider longer timeouts. The paper begs the question of, if you reach a certain threshold where you see a certain trend in fuzzer performance, do you really need more time? But like a stock market, trends can reverse. Looking at this chart here, sample chart from the paper, if you stop at different times, you would conclude that one fuzzer, AFL or AFL fast, finds more crashes than others. If you stop between this time range of 10,000 to 20,000 seconds, you would say AFL fast found 4 crashes, meanwhile AFL found 0. And same likewise here for AFL, where 30,000 to 90,000, the rest of the time, it seems to generally find more crashes. So we move on to our next topic of evaluating bug finding performance using ground truth, which is basically finding the unique bugs here, the number of distinct bugs. That's what ground truth is. What exactly does this mean? Well, in this picture here, for example, you have a buffer overflow bug. There's some input here and some input here. They both lead to a crash. Okay, so then the developer looks into this crash, applies a fix, and then you test it again. and now they both crash. They both don't crash. So even though these are technically, if the fuzzer was running, it might count these as two different crashes, even though it's technically one distinct bug, because the fix fixes both of them. However, it's very difficult to find ground truth, so because you need a developer to get in there, apply a fix, and see how many bugs that fixes, and like it is a whole process. So many papers try to skirt around it with different heuristics, like the AFL coverage profile, stack hashing, or code coverage, which I will explain pretty briefly here. So the AFL coverage profile, it basically, as you can see here, it checks the what sort of paths they took to the bug. So here, if there's some example 134, this would be one crash, and then this would be another crash 12134. The problem with this is that they both crashed at 4, but they took different paths to 4, and the AFL coverage profile wouldn't tell you that these are the same bug. It would say they were different because they took different paths. So I'm going to briefly explain a figure here. So here, these numbers is the unique number of distinct bugs that they know the program has. And then this is the number of crashes. You can see it's you would think that if you had more bugs, then there would be more crashes, right? That makes sense. If you have more bugs in the program, it would lead to more crashes. But as you can see, it's like mainly a flat line here. So there's like a weak correlation between the number of bugs and the number of crashing inputs found during a run. So the paper says AFL coverage profile might not be the best sort of metric, and this is why they emphasize finding ground truth number of distinct bugs. So let's talk about another method they talk about, stack hashing. Briefly, it just looks into the stack when a bug crashes. So I would like to ask, do you see any possible flaw in this? Well, here in this example, we can illustrate it. If you set this magical n value to 3, which is basically check 3 off the stack, you would see in this sample program, you would see this failure. It starts output, then you go to prepare, then you go to format. So anything that fails at output, prepare, format, you would be, okay, all the same bug. But say you set it at n equals 5. Now with these two functions, f and g, now there are two different bugs because one could go f, format, prepare, output, one could go g, format, prepare, output. So continuing on stack hashing, here's an example table of a fuzzer run where they know of bug A, bug B, bug C, bug D, and these are the number of hashes that it is associated with each bug. So this would be like 9 bugs they found for one bug A, 362 for one bug B. It's a drastic overcounting. Furthermore, another interesting thing you can see here with bug G and false matches, that's serial matches. What exactly does that mean? Well, I won't go too in depth here. You can read the paper if you want to know the exact details, but it basically means that bug G may never be found, even though there's a hash, because this hash could overlap with another bug, and then it would discard this bug because it's like, oh, we already found this bug. We don't need it. So that is something very problematic with stack hashing. Let's talk about code coverage. What if there's few bugs to find, right? Like you can't really count the number of crashes. There has to be some sort of metric to evaluate fuzzer performance then. This is what code coverage is. However, the paper emphasizes that you should focus on finding the ground truth but it acknowledges code coverage is a nice secondary metric to evaluate performance with. So the paper talks about what possible fuzzing benchmark could look like, as at the time of this paper, 2018, there was not really a fuzzing benchmark that they felt confident in. But to talk about that, we have to talk about some target programs. There's things like the Google Fuzz Suite, CGC, Lava M, hand injecting bugs. But let's talk about fuzzing real programs first. Here are some examples of real programs. You can read more about them in the paper. But I would like to describe what was the main paper's problems with real program fuzzing. What were the pros and cons, you could say? The pro is that it's a real program, so it's a real scenario where fuzzing would be useful. However, let's focus on the first point here. Most papers only consider a small number of target programs without clear justification of how representative this program is. Let me show you 3 graphs from the paper. They tested fuzzers on NM, object dump, and CXX filter. You can see here, AFL fast generally just finds more crashes, and with statistical significance as well. So does this mean AFL fast is just better? I mean, you did all the tests, you calculated the statistics, it should just be better. However, if you test AFL fast with different sets of programs like FF, MPEG, EF2PNG, you can read more into the paper on why AFL fast did not perform as well compared to AFL on these papers if you want more details. But you can see that these are no longer statistically significant results, and you can't really conclude AFL fast is just generally faster for AFL. So you could maybe conclude AFL fast is better for these targets, but you cannot generally conclude because these programs, there's no proof, there's no statistical significance. The other problem paper had with real program fuzzing is few papers use the same target. Let's say one paper was like, all right, I'm going to use target A, this version. Then another paper tests on target B with this version. And then another paper tests with the same target, target B, but a totally completely different version. With all these different targets, how can you compare the fuzzer results across papers? You just can't really because you're doing different targets. So these were 2 main problems they had with real program fuzzing. So what do you think would be an alternative to real program fuzzing? Well, that's fuzzing artificial programs. Like I mentioned before, some examples were CTC, LoveM. Feel free to read more about them in the paper. But the reasoning about artificials that makes them key is that when a fuzzer triggers a bug, these artificial programs tell you that you triggered this particular bug. So it's easier to find that ground truth, that distinctive bug. However, there might be some problems with artificial program fuzzing. The first one that comes to mind are these injected fake bugs. Do they translate to real bugs and real programs? Like CGC, for example, was only quote unquote 1774 lines of codes. Real world programs more complex than CGC. So does this translate? Can you use these results to prove that your fuzzer works? So with these problems with real and artificial programs, what is an example benchmark that the paper suggests? Well, we'll go through 3 points. The first thing they mentioned is that they really like the nature that artificial programs have where there's a clear indicator of when a particular bug is found. But this isn't just only found in artificial programs. It can be synthetically introduced, like in artificial programs, or maybe you just found this bug in an older version of a real program. If you have clear knowledge of these ground truth, these distinct bugs, it avoids overcounting the amount of inputs. Secondly, they suggest a large enough number of programs and these programs be large enough to represent the target as well. You can see here CGC has like 300 small programs. Google Fuzzer Suite has 25 programs. Most fuzzing papers they looked at usually tested and targeted against 25 programs. So they think around 25 programs should be what the benchmark should be. So the paper also mentions that there should be some defense against overfitting, as fuzzers might deploy a heuristic or strategy to try to game the benchmark suite. One possibility mentioned is having like a standard part of fuzzer and an evolving part of fuzzer. They go further into detail about how what of the strategies could be to avoid overfitting in the paper. But in conclusion, when evaluating fuzz testing, these are the key things to remember. Perform multiple trials. Make sure you use statistical tests on those multiple trials. Keep in mind the effect of the seed choice. It's preferable if you make the seeds available, but being well documented is also good. Furthermore, run the fuzzer for at least 24 hours. There doesn't seem to be another sort of metric that can shorten this time period. You really want to get the full trend. At least 24 hours is a good time period. And then focus on the distinct bugs, the ground truth that this paper repeatedly mentions. We The last couple of slides went over a possible fuzzing benchmark and what it could look like. Once again, focusing on known bugs, that ground truth. So, were there any flaws that I personally found with this paper? The paper is mainly an end-to-end evaluation. So it doesn't really mention evaluating specific parts of the fuzzer, like how does this mutation strategy affect the fuzzing? How does the seed choice directly affect the performance? It mentions that these things do have an effect, but it doesn't go too in depth about how or what choices you should make with these mutation and seed choices. That maybe a more specific paper would go into. Furthermore, I found that their benchmark suite suggestion, mainly the second point about having 25 programs, I didn't really find a specific reasoning rather than just following the status quo of previous of having around 25 programs. Not necessarily a flaw, but there doesn't seem specific reasoning on why that magic number works. So I was personally interested. Did they follow this advice? Let's focus briefly on some four papers that I skimmed. Fuzzbench, Magma, IoT Fuzzbench, and SOK, Prudent Evaluation Practices for Fuzzing. Fuzzbench. So this is a benchmark service that's open source. And it does follow most of the guidelines. Statistically sound. They really focus on reproducible results. They're running multiple trials. They're deduplicating bugs, find that ground truth. They also support the flexible parameter selections like seed types, empty seeds, etc. And they also provide real programs. The main thing that they differ from the paper seems to be that their primary evaluation metric is coverage, not number of distinct bugs found. Why is this? Well, they advocate for a combination of code and bug coverage. The main reasoning why is because if you just blindly take the number of bugs found, a fuzzer run could just get lucky and just not cover much of the code and just go down this path that just has a lot of bugs. This could lead to biased results. They also mention other metrics that they could use for performance, like the number of executions, the RAM usage. They allow users to import any custom metric they would like. The other paper I briefly read was Magma, and they agreed about finding bugs is the key thing. The main differentiating point here, they argued that higher coverage did not necessarily indicate better fuzzer effectiveness. So, their key thing, they were distinguishing between reaching, triggering, and detecting a bug. Reaching is just touching it, triggering is just and satisfying a condition for a crash. Detecting is the interesting one though, such as resource exhaustion bug. You get a crash, but technically the fault might not be at that time. It could have happened way earlier. And also semantic bugs, but those definitely need a reference, and those are extremely difficult to find. So for the IoT fuzz bench, this was more specific about IoT devices and it was mainly for black box fuzzing, but their performance metrics were roughly similar. The key one that's different, I would say, are speed. This one's it wasn't mentioned in the original evaluating fuzzing paper of 2018, but it's kind of obvious. If you're faster at finding bugs, it's better than finding them slower. They also mentioned having a stable process. And they also agree with Fuzzbench, where more code paths detected, more vulnerabilities that a fuzzer can find. And finally, they mention things like runtime overhead. If there's a tie between the number of crashes, whichever one had less overhead is a better fuzzer. So this begs the question between path coverage and the number of bugs found. Because two papers agree that path coverage is important to finding the number of bugs, but Magma didn't. So that's a 2-to-1. It's interesting. It's an interesting follow-up. Finally, SOK, prudent evaluation practices for fuzzing, is the most direct follow-up where they examined fuzzing papers and see if they were testing properly. Their main issue, one of their main issues was code coverage. They don't find a problem with measuring code coverage, but they think papers should explain how exactly they get this code coverage. Are they measuring paths, blocks? They need to be more specific about what this percentage means. A bigger concern is that 55% of papers were not doing multiple trials in at least one experiment. And even more concerningly, 63% were not using a statistical test at all. And then even more papers were using statistical tests or maybe not using them in the right way, leading to incorrect conclusions. So, how did they build upon the guidelines of the Evaluating Fuzz Testing 2018 paper? The key guideline that they focused on was reproducibility, open sourcing that source code and including documentation. They said fuzzers should pick representative targets that they can use to compare two different fuzzers. Furthermore, they're really keen on that documentation. Once again, document that setup. What's the runtime? What's the type of seeds you use? Regarding evaluation, they agree that code coverage and bug finding are just both important things and both should be mentioned and used to evaluate fuzzers. Finally, statistics. Fuzzing papers need to use them, and they need to use them correctly. So, to summarize, fuzzing evaluation is very difficult due to the random nature of fuzzing. However, the future fuzzing papers followed the original guidelines that were outlined for them for correctly evaluating fuzzers. Well, regarding performing multiple trials, it seems like they did for the most part, but there's a couple experiments where it seems they were lazy and didn't do at least 10 trials. Regarding statistical tests, it seems like most papers do not use them at all still, or even if they do use them, they misuse them. Regarding seed choice, they do mention what type of seeds they use, but they don't open source them, so it's hard to reproduce them. But regarding longer timeouts, most papers do run fuzzers for at least 24 hours, which is a guideline that they did follow. Finally, all fuzzing papers agree that counting distinct bugs is an important metric. Even if it isn't the primary metric they're using for evaluation, it is at least secondary. It's very important. Finding those distinct bugs is the point of fuzzing overall. That's all I have for this presentation. Thank you.